This is Saxon lesson 29A with dealing with the unit circle. Now, first thing I did is I drew a circle on a coordinate plane, and that coordinate plane is going to have, of course, my x and my y axis. And I look at it and I said, well, what if I took a distance from here to here and I put it as 1? If that 1 was a radius, it would carve out a perfect circle all the way around that was 1. If I place the vertex of a triangle right here on this circle, and I dropped a line down, the radius would remain 1, which would be the hypotenuse of the circle. Because it slid around here, you'll notice that the length of this side gets longer as it goes around, while the length of this one, let's say this triangle here, this triangle shrinks as it goes. So because of the fact that what you're doing is you're taking the angle away from one and putting it on the other. So you're taking it degrees away from one. This angle is getting smaller as this one's getting larger. And the way to remember that or think about that, all triangles have 180 degrees. If all triangles have 180 degrees, each one of the angles in it add to 180 when you sum them up. This angle here remains 90. Therefore, if you're taking away from this one, you're adding it to this one. So if I look at my standard stops, a 30 degree, a 45 degree, a 60 degree, a 90 degree stop. So if I looked at that and I said, well, what is each one of my trig functions dealing with this? My sine would be my opposite over my hypotenuse. And if I look at that and I remember that's my sine, is my opposite over my hypotenuse, the ratio of the side of the opposite is to 1, because remember this, a unit circle has a value of 1 for my radius. Notice that this will get longer as I go, the opposite does, which means that as I'm doing this, my ratio gets bigger of the hypotenuse in correlation to the opposite, because opposite on top, hypotenuse on bottom. So if I looked at that and I said, well, at 30 degrees, the ratio, this length, is exactly half of this length. But as it gets bigger, it's 0.707, so it's a bigger ratio of it. Then 0.866. Well, what happens when this line here, when my unit circle line hits the axis here, and when it does hit that axis, a unique illustration of this will occur. And that unique thing is this side here becomes the same length as the hypotenuse itself. The opposite and the hypotenuse end up being the same length. They lie on top of each other. When I take a number and I divide it by itself, I always end up with the same value, and that's 1. And that would be the sine of 90 degrees is 1. Now, I realize that you've already been told triangles can't have more than 90 degrees, and that's true. But this triangle here is unique because this 90 right here, this angle, this 90 here, ends up being on the axis itself, which means the opposite and the hypotenuse are exactly the same length because they are the same line. And it is the 90. That is the angle we're talking about. That 90 ended up lying on this unit circle or on the coordinate plane. So if I looked at the other side and I said, well, what about the cosine? Well, the cosine, remember, is adjacent over hypotenuse. Look at what's happening as this unit circle goes from 0 up to 90 degrees, and notice that this is sliding in. This length started here at 30, here at 45, and now down here at 60. Well, what happens to it when it gets to the axis itself is that it becomes 0. Because remember, it's adjacent divided by hypotenuse. Now, I want you to notice something very similar, very unique here. Notice that the 60 and the 30 have a relationship. Okay, and they flip on the 45. Okay, the 45s are the same. And then I've got the 30 and the 60 again with the relationship. So notice that one's cosine is the other one's sine. Now, the next thing that the book wants us to notice here, and this is fine, is that there is a unique relationship between the sine, cosine, and tangent. Now, if I took this, and I went ahead and wrote this out here, and we'll jump up to the book example in just a moment, but if you'll look at what I've got here, I've got the sine divided by the cosine. And what is the sine? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So when I write that like this, I end up writing it out, opposite over hypotenuse, over adjacent over hypotenuse. And I have a fraction and a fraction. If I want to cancel the lower fraction, I invert and I multiply. So I did so. Hypotenuse over adjacent, hypotenuse over adjacent. This in brackets or in parentheses here is a very, very fancy way of just saying 1. Because hypotenuse over adjacent divided by hypotenuse over adjacent is 1. It's the identity. So I can multiply the top and the bottom by the reciprocal of adjacent over hypotenuse. And when I do so, that's going to cancel out my denominator and cancel out my hypotenuse, and I'm left with opposite over adjacent. For those of you who have your trig functions memorized, opposite over adjacent is my tangent, which means the sine of theta divided by the cosine of theta is equal to the tangent of theta. Now, that's a trig identity we'll get to a little bit later, but the book wanted us to notice with the unit circle that you can do the same thing. And so what they labeled, they drew this little triangle, and I copied it up here. And this allows me to say, here's my x-axis, here's my y-axis, and there's my hypotenuse, or my radius if you want to be specific. This stays 1, and that's fine, but we're going to just say this is h. Okay? It's for hypotenuse. If I said the cosine, therefore, is adjacent, right, over hypotenuse, the sine is the opposite over hypotenuse, and the tangent is opposite over adjacent, or y over x. And we went ahead and labeled this out. If I did the same thing I did down here, and so well, what is the cosine divided, or the sine divided by the cosine? I would put y over h over x over h, and that's all I'm doing is substituting in. Here's what the sine value is, I'm putting in. Here's what the cosine value is, and putting it. And realize I have y over h, x over h. Well, once again, if I invert and multiply it, I end up with y over x. Okay? So when I use those reciprocals, y over x, well, what is y over x? There we go, that is the tangent, and that also proves it. Now, I stopped on my unit circle with writing it here. Although it would continue all the way around, staying with a radius of 1 and having this same numbers played out over and over as they dance between those two ratios. For the sine and the cosine on the unit triangle, or on the unit circle, it would go between values of 0 and 1, never growing greater than 1 and never being less than 0 for the absolute value. Of course, you're going to have some negative values in here, and that's a little bit later lesson that you'll see that they have different signs in different quadrants. But for the most part, if you look at it, the absolute value of these will vary between 0 and 1 for the sine and the cosine. And the reason being is they are all, the sine and the cosine are nothing more than ratios of what is the opposite side of the triangle doing in relationship to the hypotenuse. And then for the cosine, what is the adjacent side of the triangle doing for the as in relative comparison to the hypotenuse? And since your hypotenuse is your longest side, because that's your hypotenuse, and that's 1, you will continually have that same illustration worked out over and over and over in each one of the 4 quadrants.